All right, so again, we found the phase currents here, but we still need to find the line currents. And so just, sorry, to start off, IA, let's take a look at IA. How are we going to solve for IA? Well, we know that IA is equal to this current minus this current, right? Or the sum of the currents entering the node are equal to the sum of the currents leaving the node. And so the two currents entering are IA plus ICA, and that's going to be equal to the current leaving the node, which is IAB. And so if I want to solve for IA, I just take IAB minus ICA, right? And we can do that at every node. And so on the next slide, let me just actually bring those equations with us and just put them here. I kind of already took the liberty. I didn't want to waste too much time on this math here. This math, I took the liberty of taking the phasors and putting them into rectangular form for us already. And I have confirmed that those are the correct phasor values, so we shouldn't have to do that. If you don't remember, hopefully you do remember, that if we have something in the form of a phasor, we can put it into x plus jy form by finding x is equal to r cosine of phi, and y is equal to r sine of phi. And so that's all I did for obtaining the rectangular form of these phasors, right? Okay. And so let's go ahead and find IA. I put it into rectangular form so that we could quickly add or subtract values, right? Because it's not easy to do that with phasors. So for IA, I just determined this equation here. It's going to be IAB minus ICA, right? IAB minus ICA, which we have here. It's going to be IAB in rectangular is 10.56 plus J 7.92 amps, minus ICA, which is negative 12.14 plus J 5.185 amps. And if I put that into my calculator, right, this is just me doing KCL at this node. If I put that into my calculator, I get that IA, let me just draw a little arrow here. IA, or I guess it's a lowercase a, the way that they draw the line current. I don't know. They have some notation that they like to follow. I'm pretty bad about following notation. I should definitely be better. 22.86 angle 6.87 degrees amps. Okay, and so now, again, we have some options. We could go through and carry out the math for the rest of these, or we could go back and look at the table. And let's take a look at what the table says, because I actually haven't looked at it yet. So for delta to delta, if we're trying to find line voltages and line currents, okay. Yeah, they used some different math here. They went and just took the value here, scaled it by √3, and phase shifted it by 30 degrees. Is that kind of like what we're seeing here? Let's see. So that would mean that my 22.86 that I just calculated should be √3 multiplied by 13.2. So let me throw that in my calculator and see if that's the case. 13.2 times the square root of 3, 22.86. Okay, so that works. And then this is 30 degrees phase shifted, right? This was 36.87. This is 6.87. So we lost 30 degrees. So we can see that the table values check out, and we could just follow those values if we wish. But I'm just going to go ahead and continue doing the math I'm doing here since I've already started. IB, I think it's a good refresher to do KCL here. So KCL for IB is this node, right? We've got one current leaving here and another current entering here. So if we do the math, we're going to say the currents entering are equal to the currents leaving. We would say IB plus IAB is equal to IBC, right? And so we could find IB as IBC minus IAB. All right, so let's do that. IB is going to be IBC minus IAB. In rectangular, IBC is 1.58 minus J 13.105 amps minus IAB, which is 10.56, plus J 7.92 amps. And that means IB should be, and let's do the math here. So I've got 1.58 minus 13.105 times I minus 10.56 plus 7.92 I. I convert this to polar, 22.86. Angle, negative 113.13. And if I had to guess, I'm going to guess that that is 120 degrees less than 6.87. So let's see, 6.87 minus 120, negative 113.13. So there you go. All right, and so then I think just to save us the time, I don't think I need to do this again, but let me just do the KCL. I think it should be fairly obvious now at this point that IC will have the same magnitude, but it will be 120 degrees greater than the IA phase, so 126.87 degrees amps, right? And so those are my line currents, but I do want to set up that equation just in case KCL is still not 100% clear to you. I think that it should be at this point, should definitely be clear. That's probably one of the most important things you can learn in circuits is the KVL and KCL that you can always use. So again, we would say IC plus IBC is equal to ICA, right? The sum of the currents leaving is equal to the sum of the currents entering, and then we are interested in IC, so we would isolate that, ICA minus IBC, and so then we would come up here, we would write this out, IC is equal to CA minus BC is equal to, and then we would throw these values down in here, do the subtraction, and then we would get IC. Okay, so we found the line currents here, the phase currents here, and we're done with this problem. And we can see again that from the table, right, the line currents, or sorry, the phase currents happen to be √3 times smaller than the line currents in terms of magnitude, and they are 30 degrees phase shifted. So this is 36.87, 6.87, negative 83.13, negative 113.13, 156.87, 126.87, right? So that is proof that we did this problem correct. Pretty happy with that. And so I'm gonna go ahead and end this video. And in the next video, we'll do one last example problem just to drive these points home that these circuits may look scary, but they're really not as bad as they seem. And then we'll be done with this module. I don't like that it looks like I used the wrong size pen here. Maybe I'm typically using this one, yeah. I'll just leave that. All right, so I'm gonna wrap up this video here, and in the next video, we'll do the last example problem, and then we will be done with module 3, which is fantastic.